Hello everyone, this is Muhammad Hamza Javed and welcome to another video. In this video, we'll be building our very first neural network. So let's get started. So I have opened my Jupyter Notebook, and in this video, I'll be teaching you what keras is, how to build your first ever neural network, how to train it, how to test it, and how to get predictions out of your model. So let's get started. The very first thing we'll be doing is importing all the libraries that we'll need. From TensorFlow, import keras. From TensorFlow.keras.models, import sequential. From TensorFlow.keras.layers, import dense and flatten. Let's run this cell. Okay, so now is the best time to learn about keras. So what exactly is keras? Keras is an interface that wraps many deep learning frameworks. It runs on the top of TensorFlow, Theano, and CNDK by Microsoft. It's very user-friendly, it offers consistent and simple APIs, and enables fast experimentation. In case you are wondering, can we run keras on GPU? Yes, you can. Keras can be run on CPU as well as on GPU. Okay, so let's build the hello world of deep learning. If you're not already familiar with it, it's called the MNIST problem. It's a simple classification problem in which you classify handwritten digits from 0 to 9. So what I'll do is I'll create a digits dataset object using keras.datasets.mnist. Let's run this. Now I'll call the load data function on this object. So what this will do is this would return me two objects. The first one would be the training dataset. The next one would be the testing dataset. Okay, so now I'll further untangle the training dataset into training data and training labels. We need training data along with the labels because we need to provide them both to our network. We'll do the same for the testing dataset as well. We will untangle it into testing data and testing labels so we can test our model once it's trained. Okay, so now let's find out how many records, or let's say how many images do we have in each dataset. So in training dataset, we have around 60,000, exactly 60,000 images. In testing dataset, we have exactly 10,000 images. So usually training data is 70% and testing data is 30%, but it can vary depending upon the problem and the size of dataset you have. I have seen problems where we keep 95% dataset as training data and rest of the 5% for testing. Okay, so we have got 60,000 labels mapping exactly 60,000 images, and probably we should have 10,000 labels, and yes, we do. Okay, right now all you're seeing is numbers. I would try to show you an image, the very first image in our training dataset, so you could get an idea what exactly is in the dataset. So now I'll be using another library. It's called matplotlib. I have it installed already, but you would probably need to install it. Let me show you how you can do it. So I'll launch a new terminal. I'll clear the screen, move to my directory where my virtual environment is. I'll simply activate the virtual environment by typing source dot name of my environment, which is mhjenv/bin/activate. You can install the matplotlib by simply typing pip install matplotlib. As soon as you hit enter, it will start installing it. I'm not gonna do it because I have it installed already. So in case there are any challenges, in case you run into some errors, I would highly encourage you to let me know in the comment section below so I can find a solution for them and let you know. Let's move back to our notebook. So here what I'm going to do is display the type of our training data. So as you can see, it's a NumPy array. Let me go ahead and find the length of this dataset, and it's 60,000, which is correct. Now that we are aware it's a list, it's a NumPy array, what we'll do is we'll extract the very first element, which is going to be an image, and store it in the first image object. Okay, now I will print the shape of our first image. So it's 28 by 28. These are very small images. In production projects, you would be dealing with very high resolution images, but the process is almost the same. The next thing we'll do is call the IAmShow function on the pyplot, which we imported over here. The very first argument would be the first image that we created above, and the next argument is just a color map. So here I can see it's a handwritten 5. The reason I'm using the CMap is if I remove this snippet, this would show the image as a colored image, which it is not. We are dealing with the black and white dataset. So that's why I'm setting the color map as binary. We can do that by using CMap equals PLT color map dot binary. So here we need to scale or normalize our dataset. So why do we scale the dataset? We scale the dataset because it becomes easier for the network to get trained on it. We can scale the data either between 0 and 1, or between -1 and +1. Before we actually scale the dataset, let me show you what the maximum and minimum values in our datasets are. I'll be importing the NumPy library. I'll call the max function on our first image. It returned 255, which is the maximum value of pixel in our image. We'll call the main function, and as you can see, the minimum value of pixel in our image is 0. In order to normalize a dataset, keras has a built-in utility. It's called normalize. So we'll import the normalize function from TensorFlow keras.utils. Let's run this. We'll pass the training data into our normalize function, and this would give us training data. The training data is also called features. We'll do the same for the testing data as well. Okay, so now that our training data is normalized, we'll take the first image again. Let's see what the maximum value now is. Previously it was 255, but now we have scaled the data, so it's 0.81. Let's see what the minimum value is. It's 0. So basically our normalize function has the values in our dataset between 0 and 1. Okay, it's time to learn something new. So do you know what's the difference between feed-forward network and backpropagation? In feed-forward neural network, the input travels from input layer to the output layer in one direction. In backpropagation, there are two steps. First, feed forward the values. Next, calculate the error and propagate it to the earlier layers. Also note that the forward propagation is a part of backpropagation. So now let's build the much hyped model. It's very simple. I hope you remember we imported sequential at the very beginning of this video. We'll create a model object using this sequential class. So model is just a collection of different layers. We can add multiple layers by calling the .add function on our model object. The very first layer we'll be adding is flatten. Because our dataset is in two-dimensional, which is because it's images, we need to flatten that before we insert it into our network. The next layer would be the dense layer. We will just call the add function on our model and add the dense layer to the model. We can do that by using the dense class. We can specify the number of neurons over here, which is 128. And the next argument would be activation function. We are using relo right now. In the upcoming cells, you would know what an activation function is. The next layer would be another dense layer. We'll use the same activation function. The last layer, which is the output layer, has two differences. Number one, we are using 10 instead of 128 neurons, and there is a reason why we are doing that. We are also using softmax as our activation function. So we are using 10 because the total possible outcomes from our dataset are 10. Because the numbers we are dealing with are from 0 to 9. So it could be either 0, 1, 2, or any number between 0 and 9. We're using the softmax activation because we are concerned with the probabilities of each class. So here is our very first neural network. You can think of layers as Lego bricks. You can add as many layers as you want. You can tweak the number of neurons in each layer as well. Now let's go ahead and compile our model. And we can do that by simply calling compile on our model that we just defined. We will pass three arguments. The first one would be the optimizer. We are using Adam optimizer. Next one is loss. We are using sparse categorical cross entropy. And the last argument would be matrix. It's the matrix that we will be concerned about while training the model. So let's go ahead and compile this. Okay, so now let's learn about the activation function and loss function. Activation function. Activation function is just a simulation of neuron trigger. A neuron may or may not trigger. The activation function of a neuron defines the output of that neuron given an input or a set of inputs. Loss function. Loss function is something our model is trying to reduce while training. Loss is calculated at the end of each epoch, and an epoch is a single pass of your entire data through the network. So now you must be wondering, what function should I use for my problems? So there are different activation and loss functions for different problems. So let's say if you're dealing with a regression problem and your output type is numeric value, I would suggest you to use linear activation function with mean squared error as a loss function. If you're dealing with a classification problem and your output is binary, then I would suggest you to use sigmoid with binary cross entropy. In case it's a single label multiple classes, use softmax along with the cross entropy. In case it's multiple labels and multiple classes, use sigmoid along with the binary cross entropy. Okay, so now is the most interesting part. Let's train our model. And training the model might sound very complicated, but it's as simple as calling this fit function on our model. The very first argument we'll be passing to this function is our training data. The next argument would be training labels. The last argument is epochs. And epochs defines the number of times we want our dataset to be passed through the network. So if it's 3, that means our entire dataset would pass through the network 3 times. Let's run this. So our model is being trained right now. As you can see, we are dealing with 60,000 samples. So the first epoch is completed, which means that 60,000 images are just passed through our network. So there are two things that I want you to observe here. Number one is loss, and number two is accuracy. Our loss usually decreases as our training goes on, and accuracy increases with the training. So as you can see, our training accuracy is 98.91%, which is pretty good accuracy. Okay, now it's time to evaluate the model. Remember, we set aside two objects for testing purposes, testing data and testing labels. Now is the time to use it. And this is the first ever time we are using the testing data and testing label objects, which means that our model has never seen that data. So whatever the outcome would be, that would be unbiased. It would tell us that our model is either trained well or it needs further training. So we'll be calling the evaluate function on this model object that we trained earlier. The very first object we'll be passing is testing data. The next object is testing labels. So it's sort of like providing the model with questions and with the right answers, and then asking the model for the answers. In case the answers match with the original answers, it's a yes. In case there's a difference between original answers and the ones that model predicted, then we probably need to train our model more. This function would return validation loss and validation accuracy, and validation accuracy is something we are concerned about. So all the 10,000 images that we set aside for testing passed through our network, and the accuracy you can see over here is 97.72%, which is not bad. So let's imagine you have trained the network for a couple of weeks and now it's ready for production. So what you can do is you can save the model, and that's as simple as calling the save function on this model object. You can pass the model name in the function. In case you want to use the stored model, you can use the load model function from tensorflow.keras.models. So let's run this. The final step is getting the predictions from our trained model. So let me show you the first image that we had. It's 5, and we know that it's 5. Now let's see how intelligent our model is. For that, we'll call the predict function on the model and pass the very first element from our training data, which is the very same image that you are seeing on the screen. This would return the predictions and will display the predictions on screen. So now you can see you can't seem to figure out what predictions are. That's because these are the confidence for each of the class. In order to get the correct predicted class, you would need to call the argmax function from NumPy library on the predictions. So let's go ahead and hope it's 5. So here we go, it's in 5s, which means that our model is predicting the results accurately. So people, that's about it from this video. I hope you enjoyed this video and I hope you learned something new. In case you liked the video, please give it a thumbs up. And in case you think that the video taught you something new, please share it with your juniors and your peers. Also, if you want to see more similar videos, please subscribe. Thank you so much and I'll see you next time.